So anybody has any queries on the previous class? Please tell. Any doubts, any queries on the previous class to anyone? So this result we already mentioned earlier in the previous classes. Now we are going to prove this result now. Shall we start? So it contains two parts, main part as well as converse part. So if you consider the main part, so we assume that f is a 1-1 function. Then our claim is to prove that kernel of f contains only 0 element. Now can you tell the approach how we are going to prove this? Say. Can you tell? The same approach of group theory, what we did earlier. So we do that, we take randomly one element in the kernel, so it is becoming equal to 0. So whatever the element you pick out from the kernel, it is nothing but 0. So it means that every element in the kernel is nothing but 0 itself. Therefore, kernel is a singleton set. That is the way we prove. So if you take x belongs to the kernel as any element, then from the definition of kernel, f of x is nothing but 0 dash. As we know that image of 0 is 0, this is nothing but f of 0. Since we have taken that f is 1-1, whenever images are equal, then elements are equal. Therefore, whatever the element you are taking from the kernel, it is becoming equal to 0. Therefore, kernel f is nothing but singleton 0. Here, say. Yes or no? Right. So coming for the converse part, so here we assume that kernel f is nothing but singleton 0, and we have to show that f is 1-1. So as per the definition is considered, let us take two values in the ring. So you take that two values a, b belongs to the ring such that the images are equal. So this implies you can write this value as f of a minus f of b equal to 0 dash. Since f is a homomorphism, it is nothing but f of a minus b, and this value equal to 0 dash. So here what we observe, a minus b is an element. For this you have applied f, the result is 0. Hence, from the definition of kernel, a minus b belongs to the kernel f. Implies a minus b belongs to singleton 0, because kernel f, the set, is having only one element here. So this implies you can say that a minus b equal to 0 implies a is equal to b. Therefore, f becomes 1, 1. So this is the proof of it. So please take a note of this. If you have any other queries, you can ask. And after noting, please let me know. Right. So another property of homomorphism is, suppose we have taken f from R to R dash, a homomorphism. So let us take the picture like this. This is the ring R. This is codomain R dash. So obviously, the total images of R will be a part of R dash. So this is the image ring. This is f of R. So the total images is nothing but this part. So here, obviously, we must understand that I didn't take the onto function. So if you take the onto function, image set, codomain both are equal. So I have taken the other case. Now what happens? If you take any ideal U, the images of U also a part of the image set. So this set we call it as f of U. Since U is ideal of the domain, f of U is the ideal for f of R, the image set. So this is the importance of homomorphism. Homomorphism preserves the structure. So if you take an ideal, the image of an ideal is again an ideal. That is the importance of homomorphism. Okay? Did you get that? So here what is our intention to show? If U is an ideal in the domain, the image set f of U is an ideal for f of R. So what is the claim here? If U is an ideal in R, then f of U is an ideal in f of R. So this thing we actually want to show. So first of all, it is a non-empty set because it contains the zero element. So you are going to verify the two conditions of ideal for f of U. So let us take that x and y belongs to f of U. So what we have to prove? The difference between them must belong to f of U. So actually, what is the formal definition of f of U? It is nothing but set of all values the image values where the element is taken in U. Or generally you can write like this set of all f of z where z belongs to U. This is nothing but the image set f of U. So for every element in U, corresponding f image will be in f of U. So this is the image of U. So whenever you take two elements here, corresponding pre-images will exist in U because the elements you have taken are belonging to f of U. So immediately you can say that there exist elements A and B in U such that f of A equal to X and f of B is equal to Y. So since A comma B belongs to U, U is an ideal, so A minus B belongs to U, implies f of A minus B belongs to f of U. Since f is homomorphism, you can write it as f of A minus f of B, which belongs to U. So this equals to X minus Y belongs to f of U. So please verify the pattern. It's very simple. You take a note of this and you can ask if you have any queries. So if you take any two values in f of U, corresponding pre-image values must exist in U. Since U is an ideal, the difference between them must belong to U. So A minus B belongs to U. And what is the formal definition of f of U? For every element in U, corresponding f image should belong to f of U. Since A minus B belongs to U, f of A minus B belongs to f of U. Applying homomorphism, f of A minus f of B belongs to f of U. Nothing but X minus Y belongs to f of U. So this is the condition of ideal, the first part. Any questions for anybody? Say. Now, we are going to prove the second condition of it. The second condition of an ideal. Can I erase this? Tell me. So, coming to this part, you take an element in the set, an element in the ring. So, if I take a value y and a value r in the ring, say r dash and y dash. So, let us take that y dash belongs to f of u and r dash belongs to f of r. So for every elements, these are nothing but images, so corresponding pre-image must exist here. So therefore you can say that there exists y belongs to u such that f of y is equal to y dash, and there exists r belongs to r such that f of r is equal to r dash. So therefore U is an ideal in R, hence AR comma, you have taken Y. So YR comma RY belongs to U, implies f of YR comma f of RY belongs to f of U. Knowing that f is an homomorphism, by expanding this, f of y dot f of r and f of r into f of y belongs to f of u. Substitute in the respective values, y dash into r dash belongs to u and r dash into y dash belongs to f of u. Therefore, f of u is an ideal of f of r. So this is the proof for ideal second condition. It is very simple. For every element on the right side part, corresponding pre-image you are taking on the left side, and you are applying the respective ideal conditions on the left side. So whenever you consider f on both sides, respective solution you will get. That is the whole strategy in proving this. Agreed? Say. So after noting, please tell me. Any questions for anybody? Right? Are you getting any lag between the video and the audio? Please tell. Do you have any lag between that? Right. So in the previous class, we have proved a problem based on fundamental theorem of homomorphism. Actually, we didn't prove fundamental theorem of homomorphism on rings. So now let us prove the fundamental theorem on rings. Then let us do some on problems on homomorphism. Right? So what the fundamental theorem states, so this is the fundamental theorem of homomorphism on rings. So fundamental theorem will occur twice. One theorem in group theory and one theorem in ring theory. So we should be aware of that. What type of fundamental theorem we are going to solve, because both have similar statement as well as similar approach also in proving the problem. Right? So the statement we can write it as, if f from R to R dash is a homomorphism with kernel U, then R by U isomorphic to f of R. You please take a note of this. The statement of the theorem. Right? So here you are considering the quotient ring. Quotient ring is isomorphic to the image of the ring that you are actually proving. So if you have studied fundamental theorem in group theory already, so please tell me what is the pattern you are actually doing here to prove this theorem. What we do generally based on that proof. Any guesses for anybody? We have to show that these rings are isomorphic means we need to define a function between these two such that it is 1, 1, onto and homomorphism. You need to construct an isomorphism between the two rings by means of a function. Isn't it? Say, can you recollect the idea of fundamental theorem of homomorphism earlier? Right? So we give the function name as phi. So for the solution, you define a function phi from r by u to f of r by phi of x plus u is equal to f of x. How this function is defined? It is very simple based on the sets you have taken. How r by u is defined? It contains all cosets of the form x plus u such that where x is an element in the ring. If you take 1 in the ring, 1 plus u is the coset in r by u. If you take 0 in r, 0 plus u is the coset in r by u. So for every element in the ring, corresponding coset will belong to r by u. And how f of r is defined? It is nothing but the image. It contains all values of the form f of x, where x belongs to r. So if you take 10 in the ring, f of 10 belongs to f of r. If you take z in the ring, f of z belongs to f of r, like that. So it contains all cosets, it contains all f images. So observing the pattern of elements, I have paired them like that. Please check. Is it clear for you? Say. So first we have to prove that this function is a 1, 1 function. So let us take two cosets, x plus u and y plus u in r by u, such that phi of x plus u is equal to phi of y plus u. So how we prove that it is a 1, 1 function? Whenever images are equal, corresponding elements must be equal. So we have to bring the relation that x plus u is equal to y plus u, that we need to show. Now let us go with the simplification part. As for the phi definition, it is f of x is equal to f of y. So taking this here to the left hand side, f of x minus f of y is equal to 0 dash. Since f is a homomorphism, you can write it as f of x minus y equal to 0 dash. So x minus y is an element. To this you have applied f, the result is 0. Therefore, by definition, x minus y belongs to kernel f, the definition of the kernel. In the problem, for kernel, he has given a name u. So, x minus y belongs to u. Immediately from this result, we have discussed one coset property. So here we can write that x plus u is equal to y plus u. This type of property I already specified in the earlier sessions. And if you can observe that starting from the end, you can go to the front, the firstmost part. So this is implies and implied by, you can check that. Therefore, the function what you have defined is a 1, 1 function and also well defined. Please take a note of that. Then I will prove the homomorphism as well as onto condition. Please take a note of this. Any doubts for anybody? Are you clear with this? Right. Now, let us go with the onto property. So, what is meant by onto? Are you clear now? What I am saying? If you say that f is onto function in place of f of r, if you say that f is not onto function in place of f of r, we take all dash. The purpose of onto is this second set in the isomorphism condition is replaced with the codomain. So just simply imagine the picture such as this is r by u, this is r dash. So if it is onto, then the condition will become as r by u isomorphic to r dash. If not onto, then r by u is isomorphic. Codomain, part of codomain is isomorphic to the domain. Okay. So here we are taking the statement that f is not onto. We simply considered f as a homomorphism between the rings r and r dash only. So we didn't take onto here. Now coming back to the proof. So what you got here? Z belongs to f of r. So how f of r is defined? It contains only images. So for every element in the ring, corresponding image will be in f of r. So if you have mentioned that something is there in f of r, it means that corresponding image is there in the ring. So for some value in the ring, z is the image of that under the function f. This is the significance of f of r, because f of r is nothing but the homomorphic image. So you take a name here, say a. Therefore there exists a belongs to r such that f of a equal to z. And how the quotienting ring is defined? For every element in the ring, corresponding quotient belongs to r by u. So here a is the element in the ring, corresponding quotient is a plus u, this belongs to r by u. Now we check that for this value z, A plus U is the pre-image or not? We check for that. So A plus U belongs to R by U. So you consider phi of A plus U. As per phi definition, it is f of A and this is equal to Z. Therefore, phi is onto. Please check that. Even though if you are not able to write the data, by representing this diagram, we simply understood. For every element in the codomain, corresponding pre-image will exist in the domain. Please take a note of that. Then I prove the part of homomorphism. Is it clear to all? The onto part? Fine. Now that phi is a homomorphism, now we prove that phi is a homomorphism. So here we need to verify two conditions for phi. One condition with respect to addition and one condition with respect to multiplication. So you take the values, say A plus U comma B plus U belongs to R by U. Now you consider phi of A plus U plus B plus U. How addition of two quotients add. Fine. Any questions for this proof to anyone? Is it clear for all? Say. Any questions for anybody here on this proof? Any questions? All right then. Now let us take a problem. So here you take one ring as C plus dot. Complex numbers addition and multiplication. Another ring as M2 of R. It is nothing but set of all 2 by 2 matrices. Now the question is, I want to define a function between these two. You define a function f from complex numbers to M2 by f of a plus ib is equal to ab minus ba. In this way you define a function. Now the question is, f is an isomorphism. So we are going to verify that f is an isomorphism or not. That was the question tag. Clear? Say. What we are going to verify, right? So we are going to prove the homomorphism 1, 1 and on to as well. So if you take two values, so you say a plus ib comma c plus id belongs to the domain C, you consider f of addition. So if you have a small doubt why you are taken like this, you take that x is equal to a plus ib, y is equal to c plus id. So you are going to verify that f of x plus y is equal to f of x plus f of y or not. And also f of x dot y is equal to f of x dot f of y or not. Right. So this is the way we consider. So this is equal to, you can write like a b minus b a plus c d minus d c. So this is equal to so the first condition is verified. Please check for it. The first condition. Any questions you can ask. If you have any questions, you can ask on the first condition. After noting, please tell. Is it clear for all? The first condition? Right. Now let us go with the second condition. We start with the second condition. So this is nothing but f of, if you multiply the values, it is as per F definition, it is nothing but the matrix AC minus BD, AC minus BD, AD plus BC, AD plus BC. As per the definition of F is considered. So this you can write it as 1 1 on 2. Let us go for it. F of A plus IB is equal to F of C plus ID. From this you can say that AB minus BA is equal to CD minus DC. Equating the respective values of the matrix. From this you have A is equal to C, B is equal to D. Therefore, A plus IB is equal to C plus ID. Therefore, F is 1 1. So here F is not on 2. Why? Because so this is the complex number system you have taken. This is the 2 by 2 matrices you have taken. So in this you can take any matrix, say for example 1, 2, 3, 4. You have taken a matrix like this. What will be the complex number here? Because if you take any complex number, you cannot get the matrix 1, 2, 3, 4. So you can have matrices of the form so for this type of matrices on the right hand side, you can have the complex numbers. But if you take any different matrix on the right hand side, you cannot get a complex number. Therefore, it is not onto just a 1 1 functional homomorphism. So this thing we call it as more. We call it as monomorphism or into isomorphism. That was the name of F here. Okay. So this is one good problem, we can discuss on it. After noting, you please tell that. Are you clear? So here I want to give a new definition. In fact, a new concept in the rings. Let us start for that. So this thing we call it as Euclidean rings. So also we call them as Euclidean domain. So the definition says that we start with an integral domain. You consider an integral domain. This integral domain with an additional property, we call it as Euclidean ring or Euclidean domain. So what is the additional property is on this integral domain, we have to define a function. In other words, it is possible to define a function on the integral domain such that the function satisfies two properties, right? So that is, if we say that r plus dot is an integral domain, so define or there exists a function d from r minus 0 to z such that d of a is always greater than or equal to 0. This is condition 1, and condition 2 is given by this is condition 2. Please take a note of this. So, an integral domain with an additional property we are calling with the word as Euclidean domain. So what it is possible to find or define a function d from r minus 0 to z. Here we need to understand that in the ring R, you are excluding the 0 element and considering only non-zero values. So from r minus 0 to z, we define that. You can define the function in any manner. So the function has the property that d of a is always greater than or equal to 0. So the function always, so this function gives the result as a positive integer or 0. You will not get negative integer as a result. So if you calculate d of x, it is either 0 or greater than 0. You will not get a negative integer as a result. And if you take two non-negative values, d of a is always less than or equal to d of ab. So if the two values are not equal to 0, then d of a less than or equal to d of ab. This is first condition. And second condition, we simply call it as division algorithm. So what it says, if you take any two values in the ring, obviously the second one be not equal to 0, then you are able to find two more values in the ring such that you can write the form as dividend is equal to divisor into quotient plus remainder, where the remainder value is 0 or d of r is less than d of b. So this property is called division algorithm property. If it is possible to define such function d on the integral domain, then we call that this integral domain as an Euclidean domain. So what is the specialty of the Euclidean domain? We are starting with an integral domain. That integral domain having the additional property, we are calling it as an Euclidean domain. What is the additional property? It is possible for us to define a function on that integral domain which satisfies the two conditions, condition 1 and condition 2. So this condition we call it as the Euclidean condition or Euclidean function, you can say. That's why we are calling it as the Euclidean domain. Okay. So is the definition part clear for all? Tell me. Any questions? So here we can have one more thing, that there are a lot of questions posed on Euclidean domain. Some of them we will discuss in the class session. So one thing is, we know the integers. Z plus dot is an Euclidean ring or Euclidean domain, you can call it as. The Gaussian integers is an Euclidean domain. Every field is Euclidean ring. Every Euclidean ring is a principal ideal domain. And you have the Z of root 2 is also Euclidean domain.